Welcome to first course on power systems, and we are on module number 7, and here we will look at distribution system, various loads on power systems, and also power quality issues. And like our previous modules, this module is also very tightly connected to our reference textbook here, chapter number 8, as you'll see in next slide here. So in this module, we will look at what is meant by distribution systems and what are the various types of loads that we encounter and what are different power quality considerations, a slide or two on load management, and some price of electricity here. So we'll look at all these topics in this module. So when it comes to power systems, we know that the generation is at pretty low voltages like 20 kV, and then these voltages are transformed up and then distributed and then come to distribution system and finally to this load, which may be as low as 120, 240 volts. And by the time the electricity comes from the generator to this load, it may go through 4 or 5 transformers as we had talked about earlier. And in going through this transmission and distribution systems, approximately in North America, at least in the US, it's estimated that 9% of the power that is generated is lost. So many utilities consider 230 kV or below as transmission. So sub-transmission level voltages are considered as distribution level voltages. But some other utilities may say that 35 kV and down is what makes up the distribution system, and there we have 12 kV voltages. Secondary voltages could be as low as 600 or 480 volts line to line, 270 volts line to ground, 3-phase 4-wire. Similarly, we may encounter 3-phase 208 volt line to line, which is 120 volts line to ground. So these are some types of voltages here. When it comes to distribution system for homes, residential distribution systems, generally, single phase distribution line at 13.8 kV is sent to residential area, and locally it is stepped down to this 120 volts plus minus level here. And the neutral is grounded at the house entrance. So that's why we have this 3-prong plug where we have the line, then we have the neutral, and then we also have the ground here, like this here, right? And so this ground is carried along so that, under normal conditions, no current flows through this ground wire. And therefore, its potential cannot rise. So if you have a toaster, for example, at home, one element of the toaster is connected to line, the other one to neutral, but this ground is connected to the chassis. Okay? So that's for safety purposes. And then we also have this ground fault interrupter. So if there's a leak between the element and the ground, for example, in this toaster example I mentioned to you, this ground fault interrupter wouldn't be on a toaster, but these ground fault interrupters are connected in very sort of dangerous areas like in bathrooms and so forth, where the electric shock hazard is very serious, and because all it takes is 5 milliamps. So what we do in these ground fault interrupters is that we measure the current in both wires simultaneously, and under normal conditions the difference is 0. But under fault conditions, the current coming in one wire doesn't equal the current going out in the other wire, and that difference then causes this circuit to interrupt. So that's what this ground fault interrupter's role is. So that is somewhat shown, this system for residences in this diagram over here. Now, coming to the loads on power system, what we see here is a load duration curve. Over a 24-hour period, how does the load on a utility may vary? So just a typical load profile is shown here. Of course, it will be dependent upon the type of, from one utility to another. So here we see that, sometime here in the late afternoon or so, this load may reach its peak value, okay, whereas it may be pretty low during the night time over here. What utilities would really like is a totally constant load, but that's not what they experience. There's a great deal of difference between the peak and the valley over here, and this load factor, which ideally should be 1, comes out to be much less than 1. So this load factor would be the energy supplied in kilowatt hours by a utility divided by the energy that this utility would have supplied if this peak load had remained constant at its value all through this 24-hour period. So, there are many ways, and you can see this in this load duration curve also, that this peak value occurs where, for a very short period of time. So one of the options to make this load factor high is to use storage. And pump storage is one of the options some utilities have used. But storage is by and large still quite expensive. The other option is, of course, it's not an option, but one of the features which is very important for utilities is to be able to forecast the load ahead of time. So a great deal of money is invested in proper load forecasting. And this whole picture is getting more complicated because of the introduction of renewable energy. Because not only the load is stochastic, it's unpredictable, it's not deterministic, now this generation is also not deterministic. For example, generation by wind, and we know that wind is variable. So once again, forecasting of wind becomes very important. And it also increases the importance of storage in the system. And eventually, I think this will be implemented on a somewhat larger scale than what it is today. So let's look at this, the distribution of this load on the utility. And what we see here is that residential load corresponds to about 36%, industrial for 29%, and commercial 35% here. So these are approximate ballpark numbers, okay? And when we look at the type of load in terms of what is consuming this power, we see that motors consume about 1/2 of the load. And they also are used in this HVAC, heating, ventilating, and air conditioning. So if you combine these two here, electric motors consume about 2/3 of the power that we consume. Then lighting is about 20%, and this information technology, at least in this pie chart, is shown to be about 14%. So that will be computers and all the consumer electronic equipment and things like that. So main thing to recognize is that these are ballpark numbers. It's very difficult to come up with exact numbers as far as these different types of loads are concerned. But another possible load for utilities to consider is plug-in hybrid electric vehicles. So there's a lot of talk about plug-in hybrids, where during the nighttime these electric vehicles with substantial battery storage can be charged up, and during the daytime then possibly they can run entirely on electricity and do not have to use gasoline. So there's a great deal of excitement in this, and in fact these plug-in hybrid vehicles could be used as distributed storage for the utility, where if they are connected to some outlet or to the utility grid at the workplace, then it is possible for utilities to draw some of the energy stored in these plug-in hybrid vehicles during their peak load conditions. So they in effect they will be distributed storage for utilities. If and when that happens is not certain. Now, we should also be aware that our utilities are very, concerned about the nature of these loads and how they vary, how the real and reactive power consumed by these loads depend on voltage, magnitude. The frequency of these voltages in large interconnected systems is pretty much constant. So that's really, unless some kind of islanding occurs, that is not a concern. So it's really how the real and reactive power drawn by these loads varies as a function of the voltage magnitude. So these are the different types of loads which are listed here, and their power factor, and there is power sensitivity to voltage and reactive power sensitivity to voltage. They are listed here. So when it comes to electric heating, of course, power factor is unity, and then this power sensitivity has a factor of 2, and reactive power is 0. Incandescent lighting, power factor can be, using some capacitors and so forth, can be made to unity, but these two are given as 1.5 and 0. Well, I'm sorry, when it comes to incandescent lighting, of course the power factor is unity, because it's basically a resistance, filament resistance, okay? When it comes to fluorescent lighting, the power factor is not unity, rather it's 0.9, and usually lagging. And then the sensitivities are given here. Motor loads depend single phase, 3-phase, which type of motor you're using, and power factor is somewhere between 80 to 90%, and the power drawn as a function of voltage is in this range, and similarly the reactive power may be in this range here. But there's an increasing trend to use modern power electronics based loads, and we will talk a lot more about those in this module. And here we can make the power factor to be unity if you would like, and then even though the voltage may change, the real and reactive power doesn't change. Okay, so we'll look at that. All right, so that's really our next topic of discussion, power electronics based loads. And by and large, most of these use now this voltage link system here, and that is described over here. Here is the load which this utility is supplying, and this load here may be requiring DC or some frequency other than 60 hertz, and also a voltage which is changing. So how do we get that to this load here? So that's what is shown in this block diagram. So here the voltage is constant, and by and large the frequency is 60 hertz. Well, it may be 50 hertz in some other countries. So the frequency is constant. So what we do is we can convert this AC voltage, single phase or 3-phase, to a DC voltage across this fairly large capacitor. Generally it's a fairly large electrolytic capacitor. And then once we have this voltage here, which is a DC, we can chop it up by another converter here and synthesize whatever we need for this load here. Okay, so that's how these systems work. And these systems are growing in popularity because of the higher system efficiency that they provide. Okay, so it has been shown that if you use instead of a constant speed heat pump or air conditioner, if you have an air conditioner whose speed is continuously adjustable based on the heating or cooling demand it has, such a system could be 30% more efficient than a conventional system. Similarly, these CFLs, compact fluorescent lamps, they can be 3 to 4 times more efficient than incandescent lamps, and these require 30 to 40 kilohertz. So somehow we have to take this DC and then convert this into 30 to 40 kilohertz that these compact fluorescent lamps need. And now, as you know, there's a great deal of talk about solid state lighting in terms of LEDs, light emitting diodes, which operate on DC. All right. So other very large load on our distribution systems is in terms of motors, as we talked about. And by and large, these are induction motors. They can be single phase and they can be 3-phase. So a per phase diagram for a 3-phase motor is shown here. And if you have taken any machines course, you will be very familiar with this per phase equivalent circuit of a 3-phase induction motor. And the conventional means of controlling the speed of an induction motor, single phase or 3-phase, is by controlling the voltage across it, keeping the frequency constant. So, using a triac or something like that, back-to-back connected thyristors, we control the RMS voltage magnitude that is applied to this induction machine, which in turn controls the speed of this machine. But the frequency is constant, so the synchronous speed is constant, and as a consequence, if the speed is going down of the motor, but the synchronous speed is constant, omega slip goes up. And this large omega slip, the slip speed, if it's large, it also results in very large and I would say unacceptably high losses in the rotor circuit. But that's the nature of this conventional speed control, which is by reducing voltage. So a much better way to do that is by this adjustable frequency variable speed drives. And here we use this voltage link system that we saw earlier. So, we can synthesize, we can control the voltage that's coming to this motor here, and we can also control at the same time the frequency, depending upon what speed we want to run this at. So let's say that we control both voltage and frequency such that the air gap flux in this machine, the peak flux density in the air gap remains constant. So if that happens at different frequencies, F1, F2, F3, and so forth, we have these torque speed characteristics which are plotted over here. So the electromagnetic torque versus the speed, and assuming that the peak flux density is constant in the air gap. And that depends upon the ratio of voltage and frequency that we are applying to this machine. And if we can control both, which we can by this power electronics converter, what that means is that we can keep this peak air gap flux density in the machine constant in the air gap of this machine. So at different frequencies, we have different synchronous speeds. We can see here that at F1, the flux density distribution in the air gap would rotate at this omega sync 1, and at F2 it will rotate at omega sync 2, at F3 at omega sync 3. And let's say if you were supplying a load which offers a constant torque, constant load torque, then this intersection of this load torque line here and the torque speed characteristic would give us the operating point. So if you're operating at frequency F1 applied to this machine, then this machine would run it at this speed, and the difference of the synchronous speed and this speed is what we call the slip speed. So that's omega slip 1. Whereas if you were applying F3 to this machine, this frequency, then the synchronous speed is this, and again the intersection of this load torque and this torque speed characteristic would give us this operating speed, and again the slip speed here is the same as before. So we see here that unlike the conventional scheme where the slip speed would have gone very high, the slip speed here doesn't really change. It's this much here when the operating speed is over here, whereas it's the same here. Now the operating speed may be 1/2. Okay, so this is the way in which we keep the efficiency of this machine high, even at reduced speeds. And if we can convert this 60 hertz coming in to this variable frequency, variable voltage being applied to this machine by this system over here, if the efficiency here is high, then the overall efficiency of the system becomes much higher than in the conventional way of controlling the speed of these machines. So that's the basic nature behind these things. The other thing which we see coming in as a load on power systems are these switch mode DC power supplies. So these are used in every computer, for example, and all consumer electronics, and these nowadays are switch mode type, and this block diagram is shown over here. So here we may be required to supply very low voltage, 5 volt DC, let's say, or 12 volt DC. And what we have coming in here is 120 volts at 60 hertz. So how do we get here from here at efficiencies of 90% or higher? So to do that, what we first do, as that voltage link system block diagram showed, that we first convert this incoming AC to DC. And then we chop it up to some very high frequency AC, pass it through an isolation transformer, then rectify it here by this rectifier, and then here is a low pass filter here. Okay, so this way we can get this fairly low DC voltage, which is given as an example here at 5 or 12 volt level, in a very efficient manner with efficiency of 90% or higher. If you were to do it by linear means, we'll be lucky if you get 40 or 50% as the efficiency. So, you know, it's a big difference here. So by and large, most electronic gadgets and communication gadgets, like our computers and cell phones and everything else, they operate using this switch mode principle that I showed here. So the crux here is that we convert this into DC, chop it into high frequency AC, and then pass it through a transformer, not only for isolations and safety purposes, but also to reduce the magnitude. But this high frequency AC transformer would be much smaller at 200 or 300 kilohertz compared to a 60 hertz transformer. So this, not only it's very efficient, it's also much lighter and smaller in size, and also in cost, it'll be much smaller, much lower.